So this slide set has to do with error analysis, which is something that's important to scientific computing, although it's certainly not the core essence of scientific computing. In particular, people tend to think about scientific computing as the study of rounding errors. It's not. There's a couple of nice quotes from Nick Trefethen. One of them that I really like is, if rounding errors vanished, 95% of numerical analysis would remain. There is a lot of interesting approximation theory that goes into numerical analysis. And that sort of is related to what we think of as error analysis, but is not identical. So let's talk about what I think about as error analysis, right? Maybe the right place to start is with a very simple question. So if I told you that I had a quantity which was measured to an error of 208 kilometers per second, is that a good thing or a bad thing? Well, if it's my speedometer, that's a terrible thing, right? The cops are going to pull me over and arrest me for Lord only knows what, right? They're probably are going to arrest me for having a broken speedometer. On the other hand, if I say that's this estimate for the speed of light, well, that's not so bad, right? So the speed of light is defined to be 299,792,458 meters per second, right? Or rather, the meter is defined in terms of the speed of light and the second in that way, right? But that's pretty close to 3 times 10 to the 8th meters per second. That's what I usually remember. So the thing that I usually remember has an absolute error in it of about 208 kilometers per second. Now, if I tell you just 208 kilometers per second, that could be big, that could be small, you have no way of knowing. If I tell you, on the other hand, that the absolute error divided by the size of the thing that I care about is a relative error of about 0.07%, or 7 times 10 to the minus 4, that's a much better indicator of how big the error really is. So we're going to be mostly talking about relative error in this class. Where do errors come from? One place they come from is errors in the input, because the inputs are physical measurements, perhaps, right? Another place that they can come from is rounding error, due to the fact that computers only represent numbers to a finite precision. That tends to be, it's not unimportant, but it tends to be exaggerated by people who don't know about numerical analysis. Termination of iterations, we compute a lot of things by taking sequences of approximations, and at some point we say this is good enough and we stop, right? And there's still some error left, but hopefully it's small. Truncation error has to do with approximating continuous limits by discrete steps. So when we talk about quadrature error and error in approximating derivatives, that's truncation error. And then stochastic error comes up when we're doing, say, Monte Carlo types of calculations. And if we are trying to use randomness in a calculation, the stochastic error probably dominates everything else. If not, the other things matter a great deal. So once error gets into a calculation, it doesn't matter if we do everything perfectly after that. It's going to propagate through and it's going to affect our final results, right? So what are the basic ways that error propagates? So suppose I've got two quantities, x hat and y hat. I've got some absolute errors, e sub x and e sub y, and some relative errors, delta x and delta y, right? If I add and subtract quantities, the absolute errors add and subtract, right? The relative errors do whatever they do as defined by the absolute errors. But the thing to remember is absolute errors add and subtract, right? Now the fact that it's absolute errors adding and subtracting and that it's often relative errors that I care about will matter later when we talk about cancellation. For multiplication and division, it's the exact opposite. When you multiply two numbers, the relative errors add, right? So if I have x hat times y hat, each contaminated by each of which is the true value x or y times 1 plus delta x or times 1 plus delta y, I take the product and I get x times y times 1 plus delta x times 1 plus delta y. expand that product out, I get 1 plus delta x plus delta y plus something which, if delta x and delta y are small, then delta x times delta y is really tiny, so I neglect it typically. Right? So the relative error in the product is the sum of the relative errors in the inputs to first order, which is good enough for most practical purposes. Right? Similarly, if I look at quotients, x hat over y hat is equal to x over y with a relative error of delta x minus delta y. Right? So it's the difference of the relative errors. Now, more generally, if I'm trying to evaluate some arbitrary function, which I'll assume is at least nice and differentiable, f of x hat and y hat can be estimated in terms of a first order Taylor series, right? So it's f of xy plus the partial with respect to x times e sub x plus the partial with respect to y times e sub y, right? So all of this is sort of basic calculus, and the assumption that we're making, which is reasonable for many applications, is that we can throw away the higher order terms. They don't really matter. We can get a really good idea of what the error is doing as it propagates through our system just by looking at first order expansions, linear approximations. So let's take an example of how errors can propagate through a calculation to our detriment, right? So if I compute the integral 0 to 1 of x to the n times e to the x minus 1 dx, I can do that just by doing it for n equal to 0. And for n greater than 0, I can do integration by parts and reduce n by 1. Right? So that gives me a recurrence. E sub 0 equals 1 minus 1 over e, and e sub n is equal to 1 minus n over e sub n minus 1. Right? Now I just look at the shape of the integral, and I can tell that is bounded from below by 1 over e times n plus 1, and it's bounded from above by 1 over n plus 1. Right? So it's positive. It's actually approaching 1 over n plus 1 as n gets large. It can't be too big. I know lots of qualitative properties about it just by thinking about analysis, right? But if I start computing, I notice that things look pretty good at first, and then there's a disaster that occurs, right? So I've got something that looks perfectly accurate, it's behaving at least qualitatively correctly up through n equals 16 or 17, and then at n equals 18 it goes negative, which I know is impossible. And then at n equals 19, it blows up and it goes shooting off much bigger than anything reasonable. And at that point, even if I'm an idiot, I know that something has gone wrong, right? I just have to look at the picture and say, that doesn't look right. And indeed, it's not right. So why is it not right? Well, the easiest way to think about why it's not right is to look at what happens if we start off with slightly wrong inputs and do everything else exactly. Right? In some sense, that's the best case that we could hope for. Right? We know 1 minus 1 over e can't be represented exactly on the computer because, it's an irrational number. There's no way you're going to represent it with a finite number of digits, which is all your computer can keep around. Right? So what goes into the computer is e naught hat, which is 1 minus 1 over e plus delta. Right? And then I compute e hat 1, and that ends up having an error of minus delta. And when I compute e hat 2, that ends up having an error of 2 times delta. And when I compute e hat 3, that has an error of 3 times 2 times delta. And in general, when I compute e hat n, it has an error of plus or minus n factorial times delta. Now, delta can be really small, but n factorial gets pretty big pretty quickly, right? So n factorial times delta at some point is going to become big. And for the calculation that we had just a moment ago, sometime is around n equals 18 or 19, right? So this happens. This is something to watch out for. This is a case of an unstable algorithm. This is actually a perfectly nice integral to evaluate. And in fact, you can even use the same recurrence to evaluate it in a much more stable way, something that actually gives you the right answer. What you do is run the recurrence backwards rather than forwards. But that's neither here nor there. Right. So this is an example of something going wrong, but the problem is not actually bad, right? Now, there are cases where the problem is bad, and we'd kind of like to separate that out from the issue of the algorithm going bad, right? So a problem is said to be well conditioned if when I make small relative changes in the inputs, there's small relative changes in the outputs, right? And you can make that quantitative by talking about a condition number. So the condition number for evaluating a function, for saying y equals some function of x, is going to be the change in the output relative to the size of y over a corresponding change in the input relative to the size of x, right? An upper bound on that quantity. Now, if f happens to be a differentiable function, then delta y, the absolute change that I expect to see in y for a given change in the input, is going to be f prime at x times delta x, right? So again, we've got this first order Taylor expansion coming up that relates the errors in the input to the errors in the output, right? So a well-conditioned problem is one for which this condition number is relatively small, right? And the condition number tells you how much the errors in the input, the relative errors in the input, get magnified on the way to relative errors in the output. So a stable algorithm now is one which doesn't amplify things too much more than they would be amplified just due to the conditioning, right? So a stable algorithm is one such that the relative error coming in gets multiplied by some modest constant times the condition number to get the relative error going out, or to get a bound on the relative error going out. Okay, so that's the very basics of error analysis, error propagation, error amplification, and conditioning. Next time we'll make this a little bit more concrete by talking about where floating point errors come from and how to model floating point errors a little bit more systematically, and how we can rearrange our computations in order to avoid the detrimental effects of floating point errors.